Okay. So we are a couple, but in reality, we are 2 of the 3 authors. So I'm Piero Longara from Cineca, Jacopo, and Emanuele from IUGB for the scientific problem. So we proceed very quickly. So for this presentation, the real target is the workflow. So together with the solver SPECFEM3D. So we can see here an example of the workflow that is targeted for EUPEX and for exascale production purposes, and is composed of an integration of 2 different parts. So this is modular part and the engineering part, and this is coupled via a probabilistic ground motion scenario. So very complex workflow, and this is another picture in which a series of simulations flows into the solver to investigate via engineering study something like fluidity curve for the building. So everything is coupled with the characterization, so with the knowledge of the geological characterization in terms of faults, source parameters, geological models, and so on. But of course, the core of everything is also the most computational heavy part is the solver SPECFEM3D. It is the integral part of this presentation. So SPECFEM3D, of course, you can see, but there is a study also in the past from a colleague from IUGB that is targeting the Colosseo building. We have the reference, but is a well-known community software for solving wave propagation and exploit, of course, spectral elements, so it's both accuracy and computational efficiency on most of the tier 0 CPU, GPU architectures. So we can see here the characterization in terms of sedimentary basin, acoustic elastic, carbon acoustic elastic, and so on. Characterization in terms of different physical models. Also, there is the possibility of forward but also inverse problems. So we can solve also inverse problems. So having the characterization in terms of sources given the solution of this complex software. Concerning the SPECFEM3D, there is a huge relationship, of course, with the CHIS Center of Excellence. So I have both EUPEX, but also the CHIS hat, in which SPECFEM3D, or at least some version of the solver, is maintained. And this is a snapshot for the CHIS Center of Excellence, which is still in its 2nd phase. We apply also for the continuation of this project. So, what is the role of the investigation of SPECFEM3D in CHIS2P? That, of course, rely also on the investigation of the solver part for EUPEX. So, SPECFEM3D targeted, of course, the scientific challenges of CHIS2P, so really targeting exascale. But so it requires, for some use case, extreme computational requirements, of course, billions of users. But in particular, for some of the objectives, these rely also on EUPEX investigation. In fact, we have CPU, GPU, and system level investigation, as Matteo already presented. And in particular, the focus of for pre-exascale, exascale systems like Leonardo, Jupiter, and so on. The key concepts are the same for EUPEX, scalability, of course, because we are addressing complex scientific challenges, but also CPU and GPU efficiency and performance portability. And support, of course, the homogeneous architecture, so the solver is able to run on GPU, CPU clusters, NVIDIA, AMD already. So this is part of the investigation that we did and also presented by my colleague because, as already commented before, this is a joint interaction with EUPEX and CHEES in the sense that there is a work package targeted to exploit EUPEX and EUPilot purposes in the CHEES project. So the investigation is quite the same, of course, but related to the SPECFEM3D. The methodology, maybe we could explain a little bit, is not on the complete software environment, because this is very complex to manage for this kind of investigation, but on mini apps that rely on different physical models. So, for example, there is a list of the available mini apps for the project that can be used also outside the project, so in particular for EUPEX investigation. So every mini app has a different characterization in terms of physics, but of course also on performance. So this is the environment. So this is already, so I quickly, because already presented, so investigation been done in terms of CPU and GPU, of course, and system level matter already presented in its presentation. So for CPU, of course, mini app was investigated in terms of vectorization. So with vectorization, of course, the optimization changes. So many application mini apps that are compute bound becomes memory bound. Of course, this is an outcome already presented by colleagues, with a moderate speed up in terms of automatic vectorization for these modified mini apps. And of course, vectorization versions put higher pressure on memory bandwidth. The same presented in terms of HBM or Intel Sapphire Ravi used as a proxy, of course, because this is already available in CHEES. So in CHEES, there are investigations in terms of exascale or exascale architecture, but also as DB, like Grace Opera, and also Intel Sapphire Ravi for HBM purposes. And here we can see the speed up presented in general, but related to SPECFEM3D. And of course, so this is the investigation in terms of CPU, so more related to EUPEX, of course, but there is also investigation in terms of GPU that rely on the production version. So the SPECFEM3D is a community code targeted to exascale use cases, of course. So for GPU, that is the production version of the solver, we did an experimentation in terms of code modernization and scalability. So in particular, we can see here that the CHEES version outperformed the legacy CHEES 2P version in terms of communication efficiency. This is another relevant topic when you port the application to exascale. And in particular, up to a huge number of GPUs, so something like 500 GPUs. And more interesting is the methodology that we could apply also in EUPEX, because rely in the use of performance analysis tools like SCORP and Scalaska. And in this case, you can see the comparison in terms of performance metrics for GPU evaluation, and in particular, you can see that there is a certain gain for some particular POP metrics, so that evaluates the behavior of the entire application in terms of forms of analysis for the so-called orchestration efficiency. So the part of the GPU computation related to the transferring from the host to the device. So this is still under discussion. There is also another investigation that relies instead on the mini apps that were used also for the CPU investigation, more related to EUPEX. In this case, we use the tree architecture, tree accelerator architecture, and compare the performance in terms of performance portability. You can exploit these, and there are metrics that are different from POP metrics, but metrics usually well shaped. So performance portability will compare the performance portability of the execution of the tree version of the mini apps and produce some performance portability metric that help us in choosing the best version in terms of performance portable. In this case, we compare the A100 GPUs, Grasshopper in this case, with AMD, so basically the computing of Lumi. Okay, so now the real focus of the application is in the workflow, and so I pass the step to Laura.
Thank you, Piero. So this heterogeneity demands for methods to quickly decompose applications and orchestrate them, each part on the best suited platform. And workflow models are historically one of the ways to do this. In particular, we use these hybrid workflow models in which you take a complex application, take each step, schedule it on independent and heterogeneous hardware, and let the control plane do the dirty job. So the control plane, as a name, is called StreamFlow. It's one of the software in EUPEX WP5, and it supports several ways to write workflows, in particular the common workflow language Open Standard, which is an open way and portable way to express workflow graphs, and can run on cloud or Kubernetes, on containers, on HPC, wherever. If we take the workflow of SPECFEM3D and consider it in a purely computational way, it is a 4-step pipeline. We have a mesh of a seismic event with a composite, generate the jobs for each MPI rank, then run a distributed simulation into the wild, and convert the results into a video that domain scientists can visualize to see if it makes sense. We wrote this kind of pipeline in the common workflow language so that it is open and portable and reproducible. We orchestrated with StreamFlow so that we can scale and we can target different architectures. We used the Cineca modular HPC as a test bed to measure performance, and then we publish everything on GitHub so that data are fair and results are reproducible. This is the shape of Leonardo. It has two modules. One is booster with GPUs. The other is data-centric, so only CPUs and larger RAM, more cores, while this is mainly GPU-oriented. And then there is a storage which is in common between the two partitions, so it's a lastre parallel file system. This kind of architecture is quite diffuse, especially in Europe. It's called the modular supercomputing architecture. And since we have different steps, we want each step to exploit the most suitable part of the HPC facility. In particular, we all do AI now, so this is quite full always. This has no GPU, so no one cares, so this is always free. And we can schedule jobs very quickly here. But if we want a job that goes on GPU, here is very slow. So we want still to use GPUs when we want. So we did this hybrid scheduling. The first, the second, and the fourth steps go just on CPU, while the third, which is the SPECFEM3D simulation, that can benefit from GPUs, goes to the booster partition. This is a quite a small run with 48 core, 48 GPUs, so 12 nodes, and then 256 cores for the last one, so 4 nodes of the data-centric partition. And here is the result. So we can actually see that first and second step are trivial, third and fourth are the real bottleneck of our workflow, so the SPECFEM3D simulation part and the conversion to the video. So we can benefit from having this scheduled on the GPU part and this scheduled on the CPU part, because if we transition from one run to the real scale, which is 1760 independent simulation that must go together, these two things do not interfere with scheduling, because one goes on GPU, the other goes on CPU, and so they don't do pressure on the system. And the result should be something like this, like a pipeline of simulations that goes onto the GPUs, and a pipeline on conversions that go on the CPU partition as soon as data are available. We run just a small example with five instances instead of 1,700, because Leonardo is not mine, so I cannot take it for 1 week only for myself. And this is the result. You can see that more or less we have this kind of overlapping here, but these are only 5, so they are more or less starting all together. If you go up in the scale, there will be a lot of more pressure, so there will be more interleaved. Now, this graph is quite satisfying, but as Lucio Fontana was saying in the spatialism movement, white space is equally important than the color, and so you can see here there is a lot of blank space, and we don't want it. And why there is this blank space? Because the file system is in common, so you have put a lot of pressure on the I/O when the data are ready, and the file system is quite under pressure. And this is with 5. Imagine with 1,000. So what we want to do is possibly overlap the I/O so that this can start before, and also remove the file system from the game, and possibly without rewriting application, because this is Fortran and I don't have any idea of how Fortran is written, so I don't want to touch it. So what we do is we use another library which is called Capio, Cross Application Programmable I/O, that intercepts write and read system calls, and instead of writing and reading from the file system, forms like a pipe between producer and consumer that use network and memory. So we put the storage outside the game, and also we have overlap, because as soon as a file is ready, the consumer can start consuming it. So we don't have to write all files from the simulate and then start the conversion part. We can co-schedule them. And this is the architecture of Capio. So we have the client, which is the system called interception part, and then there is a server, a daemon, that does the communication. And still we are in experimental phase with this approach, but we estimate a 20–30% performance improvement for the single simulate convert pair without touching the code base, which is better than not. And Capio is another software from EUPEX WP5. So this is European technology, EUPEX technology, European HPC facility. So what else, no? To conclude, so SPECFEM3D, thanks to the joint effort of Pope and Cheese and EUPEX and UPilot, is portable, maintainable, exascale ready. It goes on vectorization-able CPUs and GPU accelerated machines. So when we will do the European GPU, will be ready. And then if we want to scale up to the whole HPC, Euro HPC facilities, then we have hybrid workflows, so that we can benefit from all the diversity of modern computing without touching the application. Then we solve the hardware problem in terms of acceleration, but we have the storage. So we want to put the storage away as far as we can. So Capio, transparent I/O optimization, and we have overlapping and optimization in terms of performance and latency without touching a line of Fortran. And if we take these kind of technologies, which are independent, combine them and scale the workflows, not between modules of the same HPC, but even to different HPC facilities, we can use the whole Euro HPC Federation for efficient urgent computing with European technology on European codes without touching the code itself, which is not that bad. So, if you want to know more, stay tuned with EUPEX progresses. This is a website, LinkedIn, and Blue Sky. So, or email me or email Piero, and we will answer your questions.
No, only to one remark concerning the solver and GA200. course, for the production version, there is still no activity which is related to the tuning of the production version of the machine, but there is some study in evaluating a production version of the solver targeted to COCOS. This is in the framework. That should be evaluated also tuning in terms of evaluation of mini apps, or so porting the result to the entire application, or studying this COCOS still not yet certified in the framework of cheese, clearly more suitable to performance portability studies, and in particular for the calculations. So this is still under discussion.
Very nice presentation, both of you. So thank you for the presentation. I have two questions. The first one is almost a rhetorical question. I think you will also add support for Lisa when she is delivered to Chineka, and so you will be able to. Yes, that's it.
Why not? Why not? And as soon as it comes, why not? For sure.
Okay, perfect. And the other one was about Capio, sorry.
Yeah, Capio.
Since you are, I would say, working around or completely evicting the file system, how do you handle checkpoints, potential checkpoints in the application?
So in reality, it's not mandatory to completely avoid it. The P of Capio is programmable. You can use, for example, a local storage bus buffer. You can go to the file system, but not all together, more diluted on time. Or you can completely avoid it using only memory and rely, for example, MPI techniques for tolerance. So it's up to. There are a couple of tunable things you can do.
Okay.
For performance, we completely.
Okay.
So this is not a fault tolerant run, because this is the to measure performance. Obviously, fault tolerance has overhead, but for a good reason. So.
Yes. Okay. Thank you for the answers.
Thank you. Please.
Thank you for the nice presentation. My question is, does the flow supports executing workflows across different HPC sites under different administration domains?
Yes, but so for now, the accounts are up to the user. So the user must have access to all the two facilities, and then SimFlow can orchestrate the workflow. The hope is that with this new EuroHPC Federation platform, when it will be on production, this part could be automatized from a StreamFlow plugin to the EuroHPC Federation. But for now, this is not in place already, because the EuroHPC Federation platform, as far as I know, I don't know if it is already in production from yesterday or still not in production, but it's still very new.
Or something in the past with I don't remember the name.
Here's the summit.
With federation of a small subset of EuroPC architectures, but now the project is
But what we added, the Phoenix.
Phoenix.
Phoenix. If there is something like this in place, this could be much more easy for the user to do. We did manually crafting for federated learning, federated training of LLMs across 5 EuroHPC facilities. So the Leonardo, the Lumi, the Mare Nostrum, Vega,
And Meluxina.
and probably Meluxina, yes, probably Meluxina. But this is basically, you ask for access, you obtain access, you take the keys, you find a place with internet, you connect, and then StreamFlow can handle all the stuff. But obtaining the account is up to the user, and there are five different accounts.
How do they share results between sites? I mean, is that discovery service?
Yes, it's like a meta scheduler. So it asks to the various LURM, which is the first one that is free, and then put the workload.
And for the data movement, because if you have 5, I don't know, petabytes of data.
For the data movement is a problem, but hopefully your HPC is working on large-scale interconnect direct between facilities, and so again this will be faster. So we are preparing the terrain, and then plug the optimization as soon as they come. This is the idea.
No more questions? Okay, thank you so much for the
Thank you.
presentation.